Okay, so here we are with the pumping problem that was asked about on Piazza today, or at least I hope. This is the problem that was asked about. I copied it as well as I could, but if there are inaccuracies or end up not explaining what you were wondering about, just post in the comments and we'll get that taken care of. But I think this is it. We've got this cone-shaped tank with a circular base that has a radius of 3, and the thing is 4 high, and of course the units don't matter, it could be meters, feet, doesn't matter. And we have to pump whatever is in this tank, the liquid, out of this spout, which is 1 high, and we want to figure out how much work we have to do to empty the tank. And I'm not going to go into a tremendous amount of conceptual detail, because I did that in the first video, the concept video, and I don't think people want to hear about that every time that we do one of these things. So I'm just going to kind of assume that you've seen that one, and if anything seems weird, anything that I'm saying in this seems strange, you can take a look at that video, and if it still seems strange, ask about it in the comments, and I'll clarify. But okay, so we're going to be doing this using an integral, and the way we're going to do this is we're going to slice, we're always slicing when we do integrals, horizontally. We're going to start out at the bottom here at 0 and go up to 4, which is the top, the height of this thing. So that's 4, that's 0. And at every point y, so this is the y here, at every point y along the way, we're going to slice the thing horizontally and get a cross section. And so first, let me put in the bounds of integration. This is 0 to 4. And by the way, we mentioned it's water, which has a weight of 6.25 pounds per cubic foot. It doesn't really matter though. I'm just going to say that the weight of this, whatever the substance is lambda. It's just a constant. It does not matter at all. So we're going to say it's lambda, pounds per cubic, whatever measure of length we're using. But we just need to figure out the weight because work is weight times distance. So we'll just say it's lambda, and I can immediately just stick the lambda at the front of the integral, along with the dy, which is going to go at the back here. And we're using y because it's we're going vertically from the bottom to the top, but it could be an x, it doesn't matter. But those are the two things that I can just stick in automatically. What do they represent? Of course, lambda is the weight. The dy is this infinitesimal height, the infinitesimal height of the cross-section. So the way that I'm doing this is I know that work is weight times distance. To find the weight, I have this constant lambda, and I need to find the volume. So this is the lambda is how much weight there is per unit of volume, but I need to find out what is the volume of that slice, the infinitesimal volume of that slice. And when I figure that out, it will give me an infinitesimal unit of weight when I multiply it by lambda, and then I multiply that by the distance that I'm going to have to lift that slice, and that will give me an infinitesimal unit of work. And then we're going to take this infinite sum of those infinitesimal units of work from 0 to 4, and that will give us the total work. So let's do that. In order to find the infinitesimal volume, well, I have the infinitesimal height dy, but I'm going to need the area of the cross-section. That's not going to be infinitesimal. That's the area of this disk here. That's the top view of the thing that we cut out. And we know that the area of this is pi r squared, where r is this little radius here, but we need to figure out what the r is. And the way that we do that is with these triangles here. Of course, we have similar triangles. I can look at this this kind of slice this now. Before we were slicing horizontally, now I can kind of slice this thing vertically and pull out these triangles, which correspond to this picture here. That's where they're coming from. And this triangle, I put in the spout, by the way, to make it clear that it's coming from that picture, but it's not necessary for these computations. These triangles, because they're similar, I know that the ratio of the base of the big triangle, which is 3, and my thing has become an eraser on me again, the base of the big triangle, which is 3, the ratio of that to the height of the big triangle, which is 4, has to be equal to the ratio of the base of little triangle, which is r, to the height of little triangle, which is y. And the reason is that this, as you can see from the picture, this y value is where I stopped. This is the y here. That's where I stopped and sliced the thing. So that's why I got this little triangle with base r and height y. And now, of course, this equation down here, this allows me to isolate for r. I can get r in terms of y. I get r is equal to 3 over 4y. And that gives me that gives me r squared being equal to 9y squared over 16. And this finishes the volume computation, because I already have the dy in here. This is my dy was already put in, and now I know that the area is the r squared is 9 y squared over 16. So the area of this circle, where should I put it? The area of this thing is going to be 9 pi over 16 times y squared, where y is the height at which I sliced the thing. So let me stick that in there. I can pull the constants out to the front, and I'm going to get, and this is an eraser again. I really don't know why this is happening. Sorry about that. 9 pi lambda over 16. All the constants can come out front because it's an integral. And then I have to put in the y squared. And this takes care of, by the way, the y squared times pi over 16, or 9 pi over 16. That gives me the infinitesimal volume of the cross section, or the infinitesimal area of the cross section from the top there, multiplying it by the dy. That gives me the infinitesimal volume of this thingy. And now I just need to figure out, and then multiplying it by the lambda gives me the weight. So to complete the work equation, I need the distance. Work is weight times distance. So I have to figure out, okay, how high up am I hoisting this thing, this slice that I took at a height of y here? And, well, I have to get it all the way to the top of this spout. The spout is 1 above the top of the tank, which is 4 from the bottom of the tank. So I have to get this thing all the way I have to get it up to this point, which is 5 above the bottom of the tank. And where was I when I took the slice? I was at y. So what is the distance, the total distance that I have to hoist this thing? The distance is 5 minus y. And that's what the last thing that, for the love of, there we go. The last thing that goes in here is 5. That's a weird 5. So I'm trying not to rest my hand on the screen, because I want to think that that's what's changing it to an eraser. It seems to be random, and now I rested my hand and it didn't do it. Okay, I'm just going to give up on that for now. So this is 5 minus y. That is the distance that I have to hoist it. And again, the y squared times 9 pi over 16. That was the area. Multiplying it by the dy gives me the volume. Multiplying it by the lambda gives me the weight. And then the last thing is the distance, 5 minus y. And this will give me the total work. And again, we're thinking about this as going from the y ranging from 0 to 4. And at every point, we slice it and get an infinitesimal unit of work. And we take this infinite sum of infinitely small units of work and add them up. And that gives us the exact total work that you have to do. And I'm obliged to say again, that's very hand-wavy, not exactly, not actually what's going on. It's a limit of Riemann sums. But again, this is a very useful way to think of it. So hopefully that answered the question. Hopefully it wasn't too confusing. If it didn't, of course, just add, post in the comments. This didn't make sense. I want more clarification about that point or whatever it is, and we'll get it straightened away.